Okay, good afternoon, everybody. My name is Graham Bonwick from Newcastle University, and this presentation is called Agricultural Byproducts for Shelf Life Extension. So we've heard a lot so far today about issues around sustainability, safety, security. They all come together. And for a long time, packaging has been the ignored area of these around sort of food safety, security, and sustainability. So this is the background I come from, but it's incredibly important. And we've got ongoing pressures: population growth, resources. We have longer supply chains, and they're becoming more complex, more global. And our consumers are also busier, more disconnected from things like food production, and also less food safety aware. There's a need to keep them informed. So we have a variety of other issues, not just sustainability, that we need to think about. Clearly, plastics, oil-derived polymers, perhaps to be more precise, are very much in the media. And this is certainly something that's probably going to drive a lot of change. It's certainly having an impact. Consumers are very aware of this sort of stuff. So we have everything from the macro scale, sort of plastic pollution, right the way down to the micro, and also now possibly the nano scale. And in fact, the nano scale, very small little pieces like this cropping up in fish tissues and also in the tissues of filter feeders, this sort of stuff, of increasing concern. Well, in some parts of the European Union of concern. The UK's view of this at the moment is that micro and nanoplastics aren't a threat, but I think that may change shortly. One of the issues around this is not so much that the material itself, but it's actually what might be on the surface of this sort of material. Because they tend to be hydrophobic, you get a lot of potential for toxins, persistent pollutants, etc., to actually sit on the surface, absorbed on. And these very small materials can be potentially absorbed through the gut and then deliver their load of contaminants. So this is some of the sort of side effects of exposure to these types of materials. So varying levels of concern, some very much in the public domain and consumers' consciousness, and others less so at the moment. So certainly when it comes to the consumer, they're very aware, I think, in terms of the downsides of some of these materials. And so there needs to be some kind of obvious response to keep the consumers on board. And we're seeing all kinds of potential responses. So we're seeing retailers coming up with plastic-free aisles, reductions of so many % by whenever, and some organizations not even wanting to go as far as committing to that in case they get caught out. We're seeing single polymer use, sort of statements being made, increased use of recycled polymers, and also some organizations, some companies going no plastic, completely plastic free. So all kinds of responses, all driven really by this sort of concern and a need to address consumers' awareness. But it's not just, again, the consumer. We also have some underlying directives and also now law around the need for a circular economy. So, and again, there's some very good sort of work going on, and Ellen MacArthur Foundation is being referred to as well today, an organization that's really kind of pushing for adoption of this circular approach to the economy. And this is something we've got to be very conscious of, and certainly an area for potential growth as well. So we need to look at things in terms of opportunity. So how are people responding? Well, this was in the news not so long back. This is an attempt to get away from PET. So we've got the tray here made out of tomato leaf material mixed up with cardboard pulp. So that's a step in the right direction, I guess. Now, I have to say that I'm not a complete advocate of going totally plastic-free. We have to be kind of sensible about this. I think that all materials have their uses, but certainly we do need to perhaps reduce the use of some which are of concern. So I don't want to stand here and completely be nasty about oil-derived polymers, but some of the evidence is kind of pointing in the direction that we might need to be concerned. So increasingly, I've become involved in work around trying to use natural materials as the source for alternatives to some of these oil-derived materials. And I wanted to pick one out, which is attracting a fair amount of attention at the moment. This is a material called chitosan, which is derived from chitin. And chitin is derived from various sources. It's agri-food waste sources, so things like crustacean shells are one source, but there are others, things like mushrooms and also insects as well, and their larvae can be a source of chitin, which can be converted into this material chitosan. So it's a biopolymer. It has an origin in agri-food waste as a byproduct of processing of some of these things. The production of chitosan is relatively straightforward from a chemical point of view, although as a process it's not very environmentally friendly. But what you get out of it is chitosan, which can occur in various forms, such as little particles like this. But chitosan can also be cast as films. It can be spun as fibers, and I'll talk more about that in a moment. So it's a very interesting material. And one of the added properties is that not only does it provide the basis of barrier materials, but it also has an inherent sort of antimicrobial activity as well, and even antifungal. And there's been recent publications which have nicely demonstrated that these materials damage the membranes of things like bacteria, the cell walls are disrupted, and that's the mode of action. So we get an added benefit. If we could exploit chitosan for packaging, we'd have quite an interesting potential alternative. But chitosan has its weaknesses. It's not so good on its own as a barrier material, but there's potential ways in which this could be exploited. So why be interested in things like chitin, chitosan, and other biomaterials? Well, certainly in the case of chitin and chitosan, we can start to see the beginnings of a very circular economy. So, for example, we can take our sort of food waste or agri-food waste, and instead of putting it into a landfill or incinerating it, what we can potentially do is feed it to things like these. These are the larvae of black soldier fly, and they'll consume pretty much anything organic and convert themselves, or use it to grow themselves into things from which we can derive protein. So there's a lot of interest in things like black soldier fly larvae as a source of protein at this stage, mainly for sort of aquaculture or animal feed, but could well be human in the future. So we can use this material as a source of protein and oils. We can also extract chitin out of these things, out of the larvae, convert it to chitosan. And so from this process, we can get potentially packaging materials of various types. We can produce nanofiber films, which I'll talk about in a moment. We can feed these things to fish, and we can also potentially use these materials as a substitute or replacement for pesticides and fungicides on our crops and seeds, which would be quite nice as well. And then having grown and processed and used some of these things, we can recycle and instead of dumping, feed it back. So we've got the basis of a circular economy based around biopolymers. So this is an interesting direction which we may well be heading. So this is now sort of heading into the slightly technical part now. I've been involved in the use of biopolymers and investigating their uses as alternative packaging materials or alternative packaging solutions. And one approach is electrospinning. This technology has been around for quite some time now. Sort of mid-1930s it was first described. But essentially what we have is a needle or a nozzle which is at a high voltage difference from a collecting plate, and using something like a syringe or some sort of controlled slow pump, you eject out the liquid which forms fibers as it comes out. And this is what we see typically, usually a random arrangement of nano-sized fibers. And quite a lot of materials can actually be spun into a fibrous network. This is actually used for creating things like filters. But again, it can be used for coating surfaces, for coating films, or being the film itself, and various other possibilities. And depending on how it's collected, you can either have random arrangements or even more organized arrangements. So some of the early work was done with polystyrene, which was then found to become antimicrobial, and the fibers themselves start to exhibit this antimicrobial effect, which appears to be related to their size. When we have these fine fibers, there's a high surface charge density, which is believed to be the reason behind the destruction or damage to microbial cell walls, for example. So lots of potential applications for these materials, but we don't want to be using polystyrene perhaps. So other things we can do with this process, we can spin fibers, but we can also start to spin fibers which contain various other materials as well, and these can be randomly distributed or in a more controlled fashion. And that's kind of interesting because then we now enter into the realms of creating materials which are perhaps biopolymer based, which contain other materials which could also be biological and also released from the fibers. And a piece of work that's being done, and a few people have done this now, is to encapsulate food-grade antimicrobials such as niacin, and this material is then released out of the fibers, so you get a dual effect. You have the antimicrobial activity of the fiber itself, you have a controlled release of another material which might be antimicrobial or antioxidant, again, this is, opens up various other possibilities. So some of the work that we've been doing is to try and take agri-food byproducts and see if we can make some use out of those. Again, heading towards this sort of more circular bioeconomy. So we've taken various materials and produced nanofibers from them, food-grade materials. We've also taken various types of agri-food waste and treated those, and then we've started to spin materials which are a mixture of these sorts of materials. What we've tried also to do is treat some of the agri-food waste to make it a bit more soluble, because to spray the liquid, we have to be dealing with sort of soluble or partly soluble materials, or smaller materials, so they can actually be sprayed. And so we've looked at chemical and enzyme treatments of these materials to enhance their solubility. But another reason for doing this is that some of these agri-food waste materials, if we're trying to get them to release some of their active compounds, such as polyphenols, which also have antimicrobial effects, or maybe antioxidant effects. Again, perhaps treating some of these materials chemically or with enzymes will help them release those materials. So fully trying to sort of maximize the benefits of using these agri-food wastes. So what we've got here is some images. This is on the left is some milled material, which is sort of micron sized. And then we can chemically treat this or enzymically treat it to try and enhance its porosity, so it will then more easily release some of the materials, some of the molecules that are present, such as these polyphenols. And so on the right, this is just an image of some more porous looking, in this case, tomato skins that are being milled, dried, and then treated with sodium hydroxide in this case. But ideally, we should be going towards all biological processes rather than using chemicals. So we started using this material and spinning with it to see what happens. And these are some of the sorts of films you get. So this is scanning electron microscopy, showing some of the sorts of fibers that we get. Typically, they tend to be randomly orientated, although that is something that can be controlled if you really need to. And in this case, this is little bits of milled micronized tomato skin sitting within, in this case, an alginate seaweed-derived, if you like, matrix. And we've used various materials. We've used things like the stems from wheat. We've used tomato skins and other types of waste material, which normally find very little use. It's a way also of giving them extra value, potentially. And these are being mixed up with a variety of biopolymers, and so not just chitosan, but a variety of others, which are potentially food-grade as well, to see what we get and if we can get any kind of useful performance out of them. So in these cases, we've been using alginate, chitosan, and PEO derived from palm oil. One of the things we can quite easily demonstrate is whether or not these materials have any kind of inherent antimicrobial effect. And certainly this is often the case. We can find that if we take a little piece of material, stick it onto an agar plate where we've seeded with bacteria, you find there's often a zone of inhibition around the disc. So what this is showing is that the disc material, the fiber film that we've spun, has an inhibitory effect. And again, if we incorporate food waste, such as tomato skins or other materials which have antimicrobial activity, we see this sorts of zones of inhibition, as they're called, around the disc. And this is our control showing no inhibition at all. So this is demonstrating inhibition of E. coli based on nanofibers, in this case, this is alginate, in which we've embedded dried processed tomato skin. One of the things we can do is measure the size of those zones of inhibition. So the bigger the zone of inhibition, the sort of more antimicrobial the effect. This is just to kind of demonstrate we see a range of antimicrobial activities. And this is actually a comparison of different processing regimes on that tomato skin we'd incorporated. So on the right-hand side, this is the typical zone of inhibition in square millimeters seen for, in this case, a chitosan PEO mix with nothing added to it. So as expected, chitosan in the fiber form has an inhibitory effect. But when we start adding tomato skins into it and processed tomato skin, we see a much bigger inhibitory effect. Interestingly, if we used dried material and processed it, we got a big effect. If we had wet, raw tomato skins and then chemically processed it, we got actually a reduction in effect. So we're not quite sure why, but it certainly is interesting that we can get an enhanced effect by including our tomato skins. So it kind of indicates there's some value in exploring this further. So this is inhibition of E. coli, which is a gram-negative bacterium. So we need to try it on a different type, a gram-positive, and so we've used as an alternative Bacillus subtilis as a representative species just to see what we get. And again, we tend to see the same sort of thing. We get inhibition. The way in which the tomato skin's been kind of processed didn't really seem to have a great deal of effect. But in a couple of cases, that's not totally true. Again, wet digested, wet skins processed, we lost all activity in this case. So there's something about the processing of the tomato, and what this suggests is that we may well be losing or doing something to the tomato skin, which we actually at this point in time don't quite know. We haven't gotten that far yet to find out exactly what's going on. And again, this is the effects of blending various materials. Again, our Bacillus subtilis, and different types and different blends of materials. So we've got things like alginate, chitosan, PEO, and in different proportions as well. And this is something we're starting to look at with and without tomato skin processed material as well. And again, we see quite a wide range of effects, but certainly in one case, we got a fairly good enhancement of our inhibition. And this particular one was a combination of PEO, alginate, and tomato skin. And this is something we're starting to explore further. Which sorts of materials and what combinations give us the best effects? So early stage work, this is proof of concept work that we can generate some sort of potential packaging material out of agri-food waste. So where are we going to go sort of next with this? Well, various ways in which we can go. We started micronizing cereal byproducts, so things like stems from wheat, barley, those sorts of materials, to see if that gives us any kind of effect. Rather than using chemicals to process those materials, we'd like to go down the enzyme route, so we've got a more greener processing technique. We need to examine the performance of those materials further, so we've already started looking at the antimicrobial effects, but we'd like to know more about their antioxidant properties. So again, we might get an added value from these materials if it's antioxidant or if they show antioxidant activity. We've started messing around with the formulations. We'd like to try and get films that perform better. We'd also like to understand perhaps which combinations of materials give us that microbial growth restriction. And really the next thing to do is start using these things in real life applications. So various possibilities. One is to package real foods in these films. And there's various possibilities here. One is to use this as a coating on existing materials, alternatively to directly coat food items. And so we've just started some work literally this week now. We're in the process of electrospinning fibers onto the surface of strawberries and various other items to see what that does in terms of shelf life. There is a question there which you may well be asking yourself, which is, can we eat this stuff? And that's a very good question. At the moment, chitosan, as I understand it, is not permitted for human consumption. But in reality, there's no reason why we couldn't, and things may yet change. Some of the other materials are definitely food grade, and in theory, they're safe to eat, if that's what we're going to do with them. But there's various ways in which these materials could be applied. And another possible one is to use as a coating on things like tins. So instead of putting a BPA-based lacquer on, we could perhaps be using biofilms as a surface coating. So, nice idea perhaps, using biomaterials for the basis of packaging, and whatever format that is, whether it is cast films or whether it's spun fibre films, however we decide to use these materials, there are certain concerns that need to be addressed. And again, this is kind of ongoing work at the moment. So some of the materials, some of the agri-food waste materials we might want to use may well be allergenic or contain contaminants. So, for example, agri-food wastes may come from crops, for example, that are being treated with pesticides. So do those materials survive the process? Do they transfer? Do they migrate from these materials if in contact with food? These are, at the moment, unanswered questions. The next thing is toxicity. We know that those materials, when they're in the form of nanofibers, show antimicrobial and antifungal activity. They disrupt the cell walls of those organisms and kill them. So the next question might be, well, if I was to eat something that had these nanofiber films present, what will that do? Is there a toxic risk? Now, doing a chemical analysis of those materials will probably say very little about the risk. And what we need to do really is now develop a range of probably in vitro or cell-based tests to examine the potential toxic effects of these new materials. So that's another sort of area of work that needs to be done, really, before we go much further with some of these. Another question is biodegradation. If these things get into the environment, do they break down? What we don't want to create is new nightmare materials that don't break down at all or very slow. And then, finally, will consumers accept materials derived from food waste or agri-food waste? Somebody asked me a question the other day, which was along the lines of, will vegetarians and vegans accept insect-based packaging materials? I honestly don't know, but it's an interesting question to ask before we go too far down this route. So that is something we will possibly address in the future. Certainly, there's a lot of extra work to do. This is very, very early days, but I just wanted to use this as an example of some of the work that's kind of going on in the background, which may yet lead to new solutions. So I wouldn't like to put a time scale on some of this, but you know, there are a lot of pressures out there and a lot of interested sort of parties. So this is very much a research-focused area at the moment, and a number of PhD projects have been selected for funding in this area. So I'm part of the Institute of Agri-Food Research and Innovation at Newcastle University, and we've received funding through one of our partner organizations, which is going to fund 3 PhD projects exploring some of these areas. The safety side, though, is crucial, and Newcastle University has a close collaboration through the Institute with Ferrous Science Limited, which is the UK's national reference laboratory for materials and articles in contact with food. So if you want to know whether or not substances are capable of transferring into food from packaging materials, this is really the place to go. And for us, this is the ideal partnership because they have some of the best equipment on the planet for doing this sort of work. They are actually contributing to some of these funded PhDs as well. So we have a collaboration going on which will help answer some of those questions about what's in those agri-food wastes. Do they transfer into any articles that are in contact with them, whether in the form of a film or whether in the form of a directly applied nanofiber film? So this is quite a challenging area to try and understand exactly what's present in any material, and also whether or not it will transfer is extremely technically demanding because you're starting from a position of not knowing anything about the material or what's in it. And so it requires quite a wide range of techniques. And some of the things that we might be looking for might be pesticides, they may be heavy metals, fungal toxins, depending on the source material. So there's a lot of possibilities. So to do this, to answer this sort of question is this material a risk? Can anything transfer? We need to do what's called non-targeted analysis, which basically means you need every sort of analytical tool in the box to try and find out what the answer is. So this is quite a challenging area. So that's a quick walkthrough of what we're doing at the moment in terms of biopolymers and their potential applications to packaging. I've put another opportunity to positively influence the customer. Well, perhaps consumers would like to know whether their packaging is biopolymer-based and sustainably sourced, totally recyclable, and part of a circular economy solution. That's where we'd like to head, and hopefully we'll move in that direction. And then finally, just a quick plug, starting this year, we're running a postgraduate certificate in food packaging at Newcastle University, and we're holding a thing called a Future Pack meeting, which is part of a series at Ferris Science in York. So we'll be sort of advertising those in the future. So I'd just like to say thank you very much for your attention. I hope that's been of some interest, and I'm happy to take your questions either now or later. So thank you.